Welcome back. Today we will start discussing the topic of Markov chains. The remainder of the course is almost entirely about Markov chains. We will discuss Markov chains in both discrete and continuous time, right. First, let us colloquially define what a Markov chain is. Okay. A Markov chain is a stochastic process which has the Markov property. Okay. Colloquially, Markov property is the property that the future conditioned on the present is independent of the past. Okay. So, a stochastic process which has the Markov property is a Markov process or a Markov chain. The Markov property is the property that given the present, the future and the past are conditionally independent, all right. So, this is a very colloquial understanding of what a Markov chain is. I will give a more proper definition in a little bit. So, a Markov chain or Markov process is characterized by two things. Okay. So, one is time. The time could be either discrete or continuous. Okay. So, we will study discrete time Markov chain first, then study continuous time Markov chains. Okay. The other aspect of Markov processes or Markov chains is the so called state space. State space is the set of all possible values taken by the process, by the Markov process. Okay. Again here that state space we will subdivide into three possibilities. So, let us say state space usually denoted by a set capital S could be a finite state space, it could be a countably infinite state space, or it could be a uncountably infinite state space. Uncountably infinite state space, all right. In this course, we will study both discrete and continuous time for the time axis, and for the state space we will consider finite state space first and then proceed to consider countably infinite state space. Okay. This we will do first, this we will do second. In this course we will not consider uncountable state spaces for the Markov chains, just because uncountable state space Markov processes are just technically much more complex, all right. So, we will only stick to finite and countably infinite state spaces. So, finite state space is canonically some n states, so or m states, right, some finite m number of states. So, we can just take it by default as 1 through m, and for the countably infinite case state space could be all integers or all whole numbers or something like that. Okay. Uncountable state space could be a real line or something like that, which we will not study. Okay. Now, let us give a definition of Markov chain, right. So, in discrete time, so consider discrete time stochastic process x n, where n denotes time, right, and we are looking at discrete time, and state space S. Okay. State space S. Okay. S is for us finite or countably infinite. So, a Markov chain, let me define a Markov chain definition. A discrete time Markov chain or DTMC for short is an integer time, you can just say discrete time process for which following Markov property is satisfied. Probability that x n equals j given x n minus 1 equals I, x n minus 2 equals k dot 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 till x naught. Okay, so maybe consider a discrete time stochastic process. Let me say n greater than or equal to 0. I am just starting time at 0. Okay, right. Given x naught equals L is equal to the probability that x n equals j given x n minus 1 equals I, and this should hold for all n greater than or equal to 1 and for all choices I k dot 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 L in the state space S. Okay. So, this is the Markov property in a more formal way. This is just saying that, so let us interpret this x n minus 1 equals I as the value of the state at time n minus 1, alright. You can just think of n minus 1 as the present time. Okay. Now, the value of the process at time n, the probability that x n takes the value j in the future is only dependent on the value I at the present time. It does not depend on the values in previous times, right. So, what we are saying is conditioned on the present value I, the probability that the future is equal to j does not is statistically independent of the state at n minus 2, n minus 3 and so on, okay, and this should be true for all n and all values of the past states. Okay. So, this is the Markov property. So, now, so you are looking at this probability, right. So, p x n equals j given x n minus 1 equals I is all that matters, right. So, in general this could be, let us call this p I j of n. Okay. So, this is the probability that the process goes from state I to state j at time n. Okay. Now, this dependence on n could exist in general, but if this p I j of n is simply equal to p I j for all n, then such a Markov chain is said to be a homogeneous Markov chain. If there is an explicit dependence on n, then such a Markov chain is said to be an inhomogeneous Markov chain. Okay. So, even inhomogeneous Markov chains satisfy this Markov property. It is just that inhomogeneous Markov chain, there is not that much you can say in general about their long term behavior and all that. So, whenever we talk about a Markov chain without further specification, we usually do not refer to an inhomogeneous Markov chain. Okay. Whenever we say Markov chain, typically we are talking about a homogeneous Markov chain, all right. Now, so you can think of Markov chain as a process which has one step of memory, right. So, if I am in state I at this point, I will not remember how I got to state I. The probability that I transition to some other state j is some pi j, all right. It does not matter how I got to state I. Okay. Now, so it appears that a Markov chain is a process which has exactly one step of memory. So, you recall that a Poisson process has no memory at all. So, you can think of a Markov chain as having one step of memory. Now, as it happens, you can also use Markov chains to capture 2 steps of memory or any finite k steps of memory, all right. So, let me show how that can be done, all right. Can you accommodate, so case let us say 2 step memory, 2 step, right. Suppose the process Zn has 2 steps of memory, i.e. probability that so let me just write it like this, probability that Zn equals something given Zn minus 1 Zn minus 2 dot Z naught is just equal to probability that Zn equals something given Zn minus 1 comma Zn minus 2. Okay. So, I have used some shorthand notation. So, typically this Markov property is written as shorthand, let me just mention this here. Typically Markov property is written as probability xn given xn minus 1 xn minus 2 dot x naught is equal to probability xn given xn minus 1. Okay. This is just a shorthand notation for the Markov property that we have defined above that big box. This just means that for every possible value of xn, xn minus 1 etcetera, this said shorthand, this said property holds, all right. So, in this shorthand notation, let us consider a process Zn which has 2 steps of memory, all right. So, Zn is not a Markov chain because it depends. So, the value of Zn depends also on Zn minus 2, right. It is not just a function of Zn alone, right. Now, Zn is not a Markov chain, but you consider tuples, 2 tuples in this case, right. You define let us say xn is equal to Zn comma Zn minus 1, x1 is equal to Z1 comma Z naught, x naught is equal to let us say Z naught comma Z naught. Okay. So, here I am defining these 2 tuples of these z's as a new process x, all right. For this new x process, what you can write is the following. If you consider what is this probability xn given xn minus 1 dot x naught is simply the p xn given. So, conditioned on xn minus 1 to x naught is same as conditioning on Zn minus 1, Zn minus 2, so on till Z naught, all right. And this is of course xn is just Zn comma Zn minus 1 given So, this is your xn, right. So, this is easy. Now, remember that this Z process has only 2 steps of memory, right. So, maybe I should write Zn minus 2 here, but I can forget the rest of the guys here, right. So, this is simply P xn given Zn minus 1 Zn minus 2, right. That is just probability that xn given xn minus 1, right, which means that xn, which is defined as that tuple 2 tuple, is a DTMC, alright. So, what this shows is that even if you have a process with 2 steps of memory, you can create these 2 tuples which form a DTMC, okay. This X process behaves like a Markov chain. Likewise, if you have a process with some k step memory, k is some finite integer, then you can make these k tuples and use these k tuples will become a Markov chain. So, Markov chains, bottom line is that as this calculation shows, any finite amount of memory can be modeled using a Markov chain, okay. That is the point of this brief calculation that I have showed you, right. So, the other thing I would like to mention is the representation of DTMCs using directed graphs. Okay. Suppose you are given a Markov chain, let us say xn n greater than or equal to 0 is a DTMC over a state space S. Let us say for simplicity, let us just keep a finite state space 1 2 3 dot 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 n or m, okay. So, this directed graph representation can be used for Markov chains of finite state space or even countably in finite state space, okay. The idea is the following. So, you know it's as I said, this is a homogeneous DTMC. I do not have to keep saying this. When I do not say explicitly that the Markov chain is homogeneous, we are going to assume that it is a homogeneous Markov chain. So, we are given this x n plus 1 sorry or x n, let me just say x n is equal to j given x n is equal to x n minus 1 is equal to I is some number p I j, alright. It has no dependence on n, it is a homogeneous Markov chain. So, what we will do is we will draw for each state S, so for each state in the state space S, we will draw a node, okay. Let us say 1, 2, okay. So, I have just for this purpose of illustration, I have just drawn a 6 state state space, and in this let us say, so I am going to join, I am going to draw directed edges for these nodes. These nodes are these states, okay. So, there are 6 states here. So, in this example, the states 1, 2, 3, 4, 5, 6, okay, and I am going to draw Pij's, right. So, let us say P12, P11, alright. So, these are all the Pij's, and so each directed edge I am going to draw the corresponding probability. So, here P32 is the probability that I go from state 3 to state 2, alright. So, I can draw this Markov chain. So, these are directed edges which are basically the non-zero probabilities Pij's. Okay. These Pij's are known as transition probabilities. Okay, because they capture the probability of a transition from state I to state j. Okay. And in this picture I am just drawing out the state space, all the states, in this case 6 states, and I am drawing explicitly directed edges for all those Pij's which are strictly positive, alright. For example, I may draw P63 which is the probability of transition going from 6 to 3, but if I do not draw an edge going from 3 to 6, that means that P36 is 0, alright. So, that is the way this notation works. Okay. So, I am just drawing out an example from Gallagher's book, right. Okay. Whatever, this is some example. Okay. And anything that is not explicitly drawn, for example, P66, there is no self loop. So, P55 has a self loop, that means P55 is strictly positive, P66 is strictly is not positive, it is 0. Okay. Likewise, P63 is positive, but P36 is 0, alright. So, this is a directed graph representation of a DTMC. Okay. So, you can think of, so this picture is perhaps the most easy way to visualize a discrete time Markov chain. You can think of these states as being lily pads, and the state at any time as a frog which is which keeps jumping on these lily pads. This is an analogy Professor Gallagher uses. So, you can think of the frog going from state 1 to state 2 and then state 2 to state 3 perhaps and so on. The main thing to remember is that the frog, when the frog is sitting on state 2, it does not remember how it got to state 2, right. It jumps to some state 3 with probability P23, and in more generally when the frog is in state I, he jumps to state j with probability Pij without remembering how he got to state I in the first place, right. So, you can think of this frog as jumping from these various lily pads. These lily pads are the states, okay, and the frog will jump along these directed edges with those corresponding probabilities Pij's, alright. So, this is a very intuitive way to visualize these discrete time Markov chains, especially in finite states or even countable state. You can draw a similar picture with countable state Markov chains, except that you can never really finish the diagram, right. It is an infinite number of states. So, you cannot really finish it in the countable states case, alright. Okay. So, this is where I stop for the first module.